Friends and colleagues, it's my pleasure to welcome Cristóbal Rojas from the Universidad U.Andres Bello in Santiago, who will speak to us today about statistical chaos, a new barrier in forecasting dynamical systems.
Thank you, Linda. Okay, so there. So here's the summary of the talk. I'll start by reminding the notion of deterministic chaos and the mechanism that makes individual trajectories hard to predict, and then how the statistical approach comes in and the role that physical measures plays in it. And then I'll state the result and try to give an idea of the main principles involved in the constructions. Okay, so there. So the starting point is the observation that for many practical purposes, the world around us is not a deterministic one, right? Even, for example, the roulette, even if it is a deterministic system, say that it obeys the laws of mechanics, then, well, we can represent it as a dynamical system. So this is the set of possible states. Here I mark 1, 2, the states that represent the numbers where the ball could fall. And since it's thrown by nearby positions and velocities, we can put all the initial conditions, for example, here in this little ball. And then once we pick one, it should evolve deterministically following a path and eventually falling in one of these numbers. This system then was not even a chaotic system, right? Every trajectory eventually converges to a fixed point. So there's no movement, there's no entropy generated. And so why is it that it appeared random to us? The answer is, of course, that this system is very sensitive. It is full of edges and cusps that make it very sensitive. And so when a trajectory passes by, it could go one way or another, depending on very small variations of the initial conditions. So actually the initial conditions are very mixed, and you cannot be sure if you are starting from a black one or a red one, and the trajectory actually at first look the same, but then it bifurcates, and that bifurcation makes it unpredictable. So in practice here, it's sensitivity that makes impossible to compute or control individual outcomes. All right, what if we take all the edges and cusp out of the picture and ask for smooth systems? Could this kind of phenomena still happen? And well, the answer is yes. As discovered by Lorentz, for instance, we now know very well that even simple equations can give rise to this sensitivity to initial conditions. And worse, here, the system is truly chaotic. The trajectories do not settle, and they produce entropy continuously. So this is even harder to predict. All right, so we cannot, in this case, compute individual outcomes. So what can we do, right? So for example, for the roulette, there is a simple thing that we can immediately say, right? All the numbers should have the same probability. That is some kind of prediction. So I guess the question is, how do we know that this is the case? Well, here probably because of the symmetries of these things, the way it was built, we are confident that all the numbers have the same probability. But what about for a system like the Lorentz system or other systems which do not have these nice symmetries? How can we compute the probabilities for those? Well, of course, these kind of things are very well known to practitioners, and we see these kind of statistical predictions every day. So the question, I guess, is, okay, how are these probabilities computed? How do they do this, and how meaningful are they? All right, so the principle behind this computations goes back to the an idea of Ulam in the Manhattan Project. So the story says that he was actually sick in a hospital recovering from an illness. So he has to spend a lot of days, and he passed the time by playing solitaire. So after playing a lot of solitaires, he asked himself, what is actually the probability of winning one of the solitaires? And so of course he took a pen and paper and started computing the probability. But at some point he figured that it would be too complicated. He wasn't able to do it. But then he had the idea, instead of computing analytically, well, why not just use all the games that he had played and take the average, compute the statistic, and that should be a good approximation of this probability. So he immediately thought of using this same thing to compute probabilities of other processes. And since at this time computers were more or less at hand, it would be a very natural way of going. And actually they built this Fermiac, which is an analog computer, which was used to simulate neutron diffusion processes that were fundamental in the Manhattan Project. Okay, so this is the origin of this idea. And so let's just see more or less, I mean, a little bit more detail what it is. So you have to have some way of simulating your system, even with errors. I mean, approximately, it doesn't matter. And then you choose a lot of initial conditions, and you run your simulation for all initial conditions, and you obtain a set of individual trajectories. Each of them might not be meaningful, but, oops, sorry. Each of them is not meaningful, but if you average all, then you get a statistics that is supposed to be meaningful, and that can be used to make meaningful predictions. So in order to do this, so what are the properties of a system that allow this method to work? So let's see an example. So we'll take, during the whole talk, we will look at the quadratic family. So here we have the case in which the parameter is 4, so the map is 4x times 1 minus x. This is also known as Ulam-Foy-Nonnon map, actually, because they use it as a pseudo-random generator in the project. And this is an example of a fully chaotic map. So let's have a look at this map here. So this is the usual way these maps, or the dynamics of this map, are visualized. So we see the map here. In red is the identity, and here I marked an initial condition, which happens to be here the critical point, so where the derivative is 0. And the idea is to look at the trajectory. So here we apply the map, we arrive at 1, and we use the identity to actually switch axes. And for this initial condition, we see that we arrive at 1, which is a fixed point, and then we just stay there. But this is a chaotic system. So it's supposed to be very sensitive to initial conditions. So if I change 1/2 to anything very nearby, so I made the tiniest change that I could make. And we are seeing here about 50 iterations. And it jumped from here to there. And of course, if I move a little more, it jumps wildly. So if actually we play this, we see that the trajectories are very sensitive to initial conditions. So this is indeed a fully chaotic system. Okay. So what happens if we run a Monte-Carlo simulation for this thing? So we compute a bunch of initial conditions and average where they go after many iterations. And we see that the statistics of this orbit very quickly convert to a measure, actually, which is an absolutely continuous invariant measure and has a density, which actually can be computed analytically. This is the density. And so, for instance, we see that it is more likely to find orbits near the extreme, the endpoints of the interval, which kind of makes sense because these points are fixed. And if you land, for instance, here, very, very near these points, you will escape because the points are repelling. But it might take a long time. So if you happen to fall very near one of these points, then you will spend a lot of time to escape. Then you will go somewhere else. So that is why, at least morally, you can see that it's okay that it spends kind of more time near the extremes. Okay. So this measure in particular is a measure towards which essentially, well, almost every initial condition will converge or will produce this measure. There are a few exceptions. So we saw the critical point was exceptional, and there are others, but for almost every initial condition, that will be the behavior. So this measure has this feature, and this feature is captured by the definition of physical measure. So a measure is physical if there is a positive Lebesgue measure set of initial conditions. In the case we just saw, it's the whole interval. And for each initial condition inside this set, if we look at these averages, they will converge in the weak sense to this physical measure. So it is physical in the sense that we will see it with positive probability. Well, probability 1 in the example we just saw. The set of points that actually show or follow these statistics is called the basing of attraction of the measure. And of course, these are the measures that should be used to make meaningful long-term predictions of the statistical prediction of the system. All right, so in order for this, okay, so if such a measure exists, then this is the measure we want to compute. Of course, an abstraction to this method could be that this measure do not exist, or there are too many of them. And yes, that might happen, but we are going to look at the logistic family. So as I said, so instead of looking only at parameter a equals 4, we're going to let the parameter vary from 0 to 4. And here we see, so this family is well known because it is simple enough, but it exhibits all kind of complicated behavior, including full chaos. And it also has a very nice property that for almost every parameter, the map has a unique physical measure. So here this statistical behavior is well defined for almost every parameter. So the question, of course, we want to treat is whether we can compute this measure from the parameter. Right, so here I was supposed to show how the behavior changes from ordered. So let me move the initial condition a little bit. And as the parameter increases, I'm sure you have all seen this, the behavior goes from ordered and to, well, very wild and chaotic. Okay. All right, so computability here will mean, well, let me recall the definition of computable measure. Put a very simple one here. So a measure on the interval is computable if there is a Turing machine that computes the measure of rational intervals at any given precision. So with this definition, it's immediate to see that Lebesgue measure is computable as well as any measure with computable density. So in particular, the physical measure that we saw for the U-Andres map is computable, either because of the algorithm or because the density that we have an explicit form for. Okay. All right, so the result. So the result that we have is that for this family, there exists an uncountable set of parameter values for which, well, on the one hand, there is a unique physical measure, and on the other, this measure is not computable relative to the parameter. And the main dynamical principle behind this result is the fact that this family exhibits what could be called sensitivity to the parameter of the statistic behavior. So, well, this is what I will explain during the rest of the talk. And this is the property that allows to run diagonal argument against the machines that try to compute this measure to build these examples. Okay, so before that, let me also mention that instead of the statistical description of the limiting behavior, we can also look at the spatial description, topological one. So it is known, for instance, that for this map, for actually every parameter, there is a unique topological attractor, which is actually the limit set of almost every initial condition. So it's very similar to the physical measure, but there is no statistic in this description, only a topological one. And in this setting, we showed a couple of years ago that for every parameter, this topological attractor can always be computed from the parameter. There is no such non-computability phenomenon. Actually, for almost every parameter, the attractor is even computable in polynomial time. However, there is an exceptional set, a zero measure set of parameters for which the attractor can have essentially arbitrarily high complexity. Okay, so let's back to our main result. So as I said, the main dynamical principle behind is this sensitivity, this statistical sensitivity to parameters. So this is the technical statement that expresses this. So this is the only technical slide that I have. So the result, or the technical result, it says that there is, of course, we will play the game near 4, in the region where the dynamics are complex. So there is an uncountable set of parameters, and there is an infinite sequence of periodic points. So these periodic points are persistent in the sense that if we move the parameter, the periodic orbits remain. They move, but they're still there. And for this sequence of periodic points, we have the following. For each of these parameters, this is a way of denoting the limiting measure when I start at X. All right, so the first point is that the limiting measure of almost every initial condition is the same as the limiting measure of the critical point. So this is a very important thing because we are going to use to control the orbit of the critical point in order to produce the physical measure, and we need all the rest of the points to follow this. And okay, and the limiting measure of the critical point is going to be, therefore, since every point follows the same statistic, it's going to be a physical measure. The second point is that this physical measure is charges only the periodic points in these sequences. And moreover, here is the sensitivity. If we choose an arbitrary combination of weights for these periodic points, the periodic orbits, then inside our set, there is a dense subset of parameters that actually realize this assignment of weights. So here you see that if you change the weights, then arbitrarily nearby, you can find a different parameter that will realize those weights. So you can change the physical measure by a considerable amount by perturbing the parameter arbitrarily with arbitrarily small perturbations of the parameter. All right. Okay, and this is what we are going to use for the construction. I'm going to show that at the end. And the main part of the talk is going to be to explain this result, and we'll do it for a particular case. So before starting with the construction, I'm going to state this principle, which is will be very important for us. So as I said, this big omega here, it's a notation for the limiting measure when I start at X. And the principle here is that suppose that the critical point is periodic. So yeah, it's periodic. Then for these cases, there is always exists a unit physical measure, and which is actually the measure supported on this periodic orbit. And so in particular, almost all other points in the interval will follow the same statistics. This always happens when the critical point is periodic. Actually, I can illustrate this here. So I've chosen a parameter here for which you see the critical point is periodic, it's period 2. And if we move the initial condition, we see that they all converge to that thing. So the physical measure is also going to be supported on these 2 points. So a combination of 2 masses. All right, this is the fact 1. Okay, and the strategy then to build this set of parameters where the statistical sensitivity occurs is going to gain control on this critical orbit. So this is going to be our leading orbit. All right, so the way of explaining that technical result is going to be by producing one example. So we are going to produce a physical measure, which is going to be support on a period 3 orbit. Actually, this is kind of weird because this orbit is going to be a repelling orbit. So nearby points will escape from this orbit, but somehow the statistics will be concentrated on them. So the idea is that points will spend more and more time near this orbit. So in the limit, the statistical measure will be supported on them. All right, so we'll start with, so here we have a map, and we're in blue, we're looking at the 3rd iterator of this map, so G, which is F3. And here I choose a specific one that has the following property. So for this parameter, for the parameter of the blue map here, the critical point has this orbit. It goes 2 steps and then falls into a fixed point here. This fixed point, I'm going to call it beta. And this is, so it is a fixed point for the 3rd iterate. So it's a period 3 orbit for the original map. And that period 3 orbit is going to be the support of the physical measure that we are going to build. So this is what we want to achieve. All right. So first of all, so here, this is our starting point. So the first observation is that this fixed point, well, it's a repelling fixed point. That means that nearby points escape, and you can see that because the derivative here is greater than 1. And if I move the parameter, so if I shift the blue graph up or down a little bit, well, it will still cross the identity, so the fixed point will persist. The difference is that if I move the parameter, that point still persists, but the critical point do not hit it exactly anymore. It falls nearby, and therefore it eventually escapes and goes somewhere else. All right, very good. So now I want to change the parameter again in order to close this trajectory into a periodic one. So I can do that because I haven't changed the parameter yet, but now we are visualizing the 2nd iterate of the map. And you can see that over this region here, there is a small interval whose image is large enough that it will contain the critical point. And so all what we have to do is to choose the parameter so that when we continue this trajectory, well, it will follow somewhere here, and we can control this because of the great sensitivity that we have. So we do it, and we close the trajectory. So we move a little bit our parameter and achieve this. So now the trajectory of the critical point has come back to itself, and it is a periodic trajectory. So what is the physical measure at this point? Well, as by fact 1, we know that since the critical point is periodic, the physical measure is exactly the measure supported on this trajectory, the trajectory of the critical point. And but the trajectory of the critical point contains more than only these 3 points that we want. But we see that the orbit, the measure is already kind of given a lot of weight to these 3 points, but there is a lot of other stuff. So now we iterate this process. Yeah, so this is more a Monte-Carlo simulation for this stage of the construction. So we are achieving what we want, but we're not quite there yet. So now what do we do? Well, we perturb again, and we make it in such a way that the critical point, instead of returning exactly to itself, it misses, and it continues, but it does it in such a way that it lands even deeper inside this or near this fixed point. So it will take even longer to escape. And therefore the new trajectory will spend more time near this fixed point, and the measure will charge even more this orbit. So we make an even longer cycle, and of course we make it return to itself again. And now we have another periodic orbit for the critical point, which therefore supports a physical measure. And now we see that the measure is way more supported on the 3 points that we have. So we continue this, and in the limit, then we obtain exactly what we wanted, a parameter for which the physical measure is supported on this period 3 repelling orbit. So again, when you look at orbits here, they spend time near these things and they go away, but they do it in such a way that they spend more and more time near these points, and the limiting statistic is just the mass point over these 3. So the idea is then, okay, so this same game can be played for other periodic points. And so we need to have an infinite sequence of periodic points that persist, and then we can generalize this construction and to actually achieve essentially any statistic that we want on them. All right. Okay, so how do we use the this theorem to build the non-computable physical measures? All right, so this is a diagonal argument. All right, so it goes like this. It's not new. So we enumerate all the machines that say compute some probability measure relative to the parameter, and we choose an interval in the name of the first machine, and let the machine, or ask the machine, to compute the physical measure at some precision that we choose. So the idea is that, okay, the point is in the domain of the machine, so it eventually halts, and it gives an answer. But at that point, of course, it only knows a small interval of the parameter. And if the machine must also halt and give the same answer for any other point inside this small interval. So what we do is that we apply our key theorem, and since we have a lot of points inside, actually more or less everywhere, we can pick points inside this same interval for which the physical measure is going to be very different, in particular incompatible with the answer of the first machine. All right, so we just took care of the first machine, and then we can do it for the next. Right, so but the idea is that the parameter, we have identified a set inside of which all the parameters will have a physical measure, which will be significantly different from the one computed by M1. And now we iterate this. So we choose a different parameter inside the set that we already have in order to keep the fact that the first machine gave the wrong answer, and which is inside the domain of the second machine, and and ask this machine to compute the measure at some smaller precision. And then again, when the machine halts, it only knows a small interval containing the parameter, and it must give the same answer for any other interval inside. And therefore, we can use the theorem again to fool this machine and find a different a parameter which is nearby, for which the physical measure is very different, not only from the one computed by M2, but also by the one computed by M1. And so continuing in this way, we iterate this process, and at the end, we obtain a parameter such that for any of the machines, there is a precision below which the physical measure is going to be incompatible with whatever that machine computes. And therefore, no machine can compute correctly the physical measure for this parameter. And well, because of the choices that we have in the construction, the set of such examples is uncountable. All right, so that is the end of the proof. Oh, that was quick. All right. So, what questions are left? Well, a lot of questions I would like to work on or see people working on. So, for instance, there are exceptional behaviors for the logistic maps with respect to the parameters, but there are theorems that say that for almost every parameter, things are good. I would like to see how this relates to parameters which are algorithmically random. So for instance, the examples that we have, we know that they are exceptional. Will it be true that if we pick an algorithmically random parameter, then the physical measures are computable? Are the behavior of this map predictable? So there is a dichotomy for this family, which is actually conjectured to be true for any other meaningful family, that says that with probability 1, a map here will be either regular, meaning that it will converge to a finite set of points, so the attractor is just finite, or stochastic, meaning that it has very good statistical properties. So not only existence of physical measures, but only decay of correlations, and so in all the properties that make the prediction easier and plausible. So what are the, what kind of algorithmic randomness gives the right condition to imply these things, for instance? And the other direction that I think is interesting is to study the extent to which this non-computability or even high complexity can be prevalent in this family or other families. For instance, we know that, okay, in this family, non-computability is quite exceptional, but there are other results that suggest that in higher dimensions, such constructions could be possible, and maybe even in a generic way. So it is possible, it is plausible that for a generic set of parameters, say in 2D, for polynomials in 2D, we have this kind of non-computability phenomenon. And of course, we can ask for less, maybe just non-polytime computability. That's bad enough. And of course, there is a lot of more parameters for which that could happen. And I wonder whether that could happen maybe with positive probability. I think these questions are, well, difficult, but really interesting and worth pursuing. All right, that's the end of the talk that I prepared.
Thank you.
You're very welcome.
Are there any questions?
I would have one, or probably two at least. It kind of feels that that's a statement that you can really get all kinds of distributions over your fixed points in a dense set. That seems like it should be sufficiently powerful to give you more than just is not computable. Have you tried to push that up?
That's a good question. I think so too, but I haven't tried hard enough yet. I'm kind of more intrigued by what makes the physical measure computable. So I'm looking that for now. And yes, but that's a very interesting question. I think that the answer is yes, you can do worst. However, at first sight, this high sensitivity or discontinuity of the physical measure also happens for the attractor as a topological object. But somehow there, it's not possible. So it can't. So the actual sensitivity or the structure of the sensitivity plays a role in allowing you to build such counterexamples. So that was the first question?
Yeah, I was just giving someone else the chance to butt in, but Now I actually have a question 1.5. So when you're saying that the kinds of discontinuities also happen for the topological attractor, does that mean that, in a sense, that it's true that the attractor is always computable relative to the parameter, but it's just not true that the map from parameter to attractors is a computable function? Or
right. So yeah. So the function, that last function that you mentioned, is not continuous. It's very discontinuous. Yeah. So it cannot be computable as a map. So you have three kinds of topological attractors. Actually, we can more or less see them here. So one is a finite one, so like here, okay, easily computable. Another one is like at the end, so it's just one interval or finitely many intervals which are disjoint. So the union of finitely many, and those happen to be also easy to compute. But then there are the ones called Feynman attractors, which are like in the edge of chaos. So so these attractors have a Cantor-like structure, and those are harder to compute. So there are, okay, interestingly, for the last one, so the ones that are hard to compute, a single machine from the parameter can compute them all. But these are also the ones that exhibit the high complexity phenomena. And the others are actually, essentially, you need a different machine for each of the pieces. For example, here, in this interval, of course, you need one machine. But since these windows get smaller and smaller and mix in a fractal way, you need one machine per region, more or less. So countably many. And the information, the crucial information is a certain period that underlies the structure of the attractor. In that period, it's an integer that you cannot compute from the parameter.
And then my question too was, do you know some upper bound for the like Weierach degree for the map from parameter to physical measure?
Yes, so trivial upper bound is, well, the measures are limit computable. So you do not have the rate, but you do have a sequence of measures that converge to it in each case.
Okay.
I have a question. What happens if you incorporate some uncertainty about what the parameter is, in the sense of maybe say the parameter is some, like, kind of tight around a point?
Right. That's very good question, because that somehow get closer to what people would experience if they actually try to do this, right? And the answer is that there is a positive measures set of parameters for which, if you try to do that as you describe it, then what you will see will be, with positive probability, far enough from the actual measure. So said another way, for this set of parameters, if you pick any of them, then nearby there is a positive measure set of parameters, such that for all of them, the physical measures are far away from the one that the parameter that you are interested in. And you can actually observe this with a single function, a single observable that could be the identity. And you could fix the resolution of being away in advance. So you can pick a resolution and observable, and then there exists a positive set of parameters, a positive measure set of parameters for which this non-approximability happens. So from the computability, the non-computability result is very strong. It's too strong, that is why it's exceptional. But if you ask only for approximate computability in this sense, then you see non-approximability with positive probability. Yeah, that's a very nice, very good, interesting question.
All right, so hearing no more questions, I will say thank you to Cristóbal again for a very nice talk.
Thank you. My pleasure. Hope you enjoyed.